In this video, we're going to continue discussing transformations of functions. We're going to focus on reflections and types of symmetry. So let's start with reflections. We can reflect a function in two ways that we're going to focus on: over the horizontal axis or over the vertical axis. So they use the square root function to demonstrate this again. So vertically, or over the horizontal axis in this case, that's what the reflection visually is going to look like. But let's look at and notice that what's really happening is that each output value, maybe not so much at 2, but 4, each output value is becoming a negative. So instead of going to positive 1, it went to negative 1. Instead of going to positive 2, it went to negative 2. And that's kind of how that ends up playing out. That's a vertical reflection. So what that does then is that takes our original graph, and they call it V of t when they wrote it, and they take all the outputs and they make them negative. So we basically throw a negative in front of the square root. A reflection over the vertical axis would look like this. So this time, the thing that's becoming negative are the input values. So instead of being at 1, 1, it's negative 1, 1, right? So it's going from negative values instead of positive values. And kind of what we talked about last time with the vertical shifting, what that means then is that it's not affecting the outputs, it's affecting the inputs. So the equation for this, we'll use h of t this time, is going to be a negative in front of the inputs, in this case, t. And that's how we represent that. So let's write that in general. Oh, no, sorry, before we do that, these transformations can affect the domain and range of the functions. Okay, so that's kind of an important thing to note, that we could possibly change that domain and range because of this. So for the first one here, this first equation, the range was affected. So originally the range went from 0 to infinity. It never went to the negatives, and it just keeps growing upward. That's this range. Sorry, the range over here. I should write it with the equation I'm talking about. But the range in the transformation is now negatives. So it's actually negative infinity up to 0. So it's doing negatives instead. That's how the range changed. In the second graph, when we're looking at horizontally, this one, the domain is changing. So over here, the domain is going from 0 to infinity. But here, the domain is switching and it's going to the negatives. So it's going to go from negative infinity up to 0. So it can affect the domain and range when we do these transformations. Okay, now let me go ahead and write the in general formula for reflection. So given function f of x, we define g of x as negative f of x, which basically changes the output values, and that ends up being a reflection across the x-axis or the horizontal axis. If we define g of x, where we apply the negative to the x, that affects the input values, and that ends up reflecting across the y-axis. So applying it to the output values is a vertical reflection. Applying it to the inputs is a horizontal reflection. All right, so let's see how that plays out in a table example. So this is going to be fun. The first one's pretty easy if we're going to do a horizontal reflection. That one's not too exciting. So here, let me draw that out. So x, and then let's see, we have a g of x, and then we have an h of x. Okay, so for g of x, we are applying the negative to the outputs. So all of the inputs remain the same, but the outputs become negative. Now, unlike the horizontal shift, this isn't too complicated. When we apply the negative to the inputs, that means then that the inputs become all negative, but the outputs stay the same as the original function. And that's how that would work out. So that's kind of nice. Pretty straightforward that way. Let's look at an example. So this is a common model for learning has an equation similar to negative 2t to the negative t plus 1, where k is a percentage of mastery that can be achieved after t practices. So k is somehow how much you've mastered something based on how many practice sessions you use or perform. So they've given us the equation or the graph of 2 to the t. That's this graph here. So this is f of 2 raised to the t. So our inputs in this case are the exponents, become the exponents of this. And they call this an exponential equation. So what we want to know is what has occurred on k of t, how they've changed the equation. Well, first thing I notice is they threw a negative in the front. So a negative here in the front, that's a vertical reflection. So putting a negative in the front is a vertical reflection. Or another way of saying that is it's going to reflect across the x-axis. Then they put a negative next to the t. So a negative next to the t is also a horizontal reflection. So it's going to reflect across the y-axis as well. So reflect over y-axis. And then last, they added a 1. That plus 1 is a vertical shift, which is going to shift it up 1 unit. So I'm going to perform these shifts or changes to this negative, to 2t, kind of see what that looks like. And I might do it in steps to kind of help me out here. So first thing I'm going to do is I'm going to reflect it over the x-axis. So this thing goes through 1, 0. So I'm going to have it go through 0. It goes through 0, 1 on the y-axis. So I'm going to have it go through 0, negative 1 on the y-axis. That's this point right here. All right. I also notice it's going through 1, 2. So I'm going to have it go through 1, negative 2. And another point I noticed that's kind of easy to see is 2, 4. So I'm going to have it go through 2, negative 4. All right, so I'm going to kind of replicate this. Now, just to kind of show, right here, it's at about halfway. At negative 1, it's about halfway. So that would be halfway on the negative. All right, so I think that's good enough for me to draw. So let me go ahead and sketch it. Okay, so that's the first shift. That's the vertical reflection. Okay, so now I want to do a horizontal reflection, which means I'm going to change all of the input values to negative. So this one doesn't change because it's on the y-axis. I'm going to leave it right where it is. But this one is going to flip over here. This is going to flip over here. And this is going to flip over here. So I've basically taken all my points and I reflected it across the y-axis. And that's going to look like this. Okay. So the green graph is this change. The red graph is the vertical reflection. So now the final one, the vertical shift, I'm going to do in blue. So we're going to shift it up 1. So I'm going to take all of my output values on the green graph and I'm just going to go up 1. And that is the final. Oops. Shouldn't have crossed. That is what the final graph looks like. So this is K of T, the resulting graph. Now, you could have done the reflections or started some of those reflections on the original graph so that your final graph is just K of T. You could just erase the changes you made, like the green and the red. I mean, I could just erase those so that the final graph is what I'm seeing. But there's nothing wrong with kind of stepping through it. Here, I don't want to erase that red dot because I think it'll erase the whole thing. But there you go. That's kind of how I would step through those transformations. All right, let's talk about symmetry. So there's some types of symmetry we're really interested in. And the first type is where we look at this kind of patterning across the axes, and in this case, the origin. So we're also interested in reflections across the origin. So if we look at f of x equaling x squared, or f of x equaling the absolute value of x, those particular graphs are symmetric about the y-axis. So in other words, they look like mirror images over the y-axis. And let me just kind of do a rough sketch. So x squared, that's the parabola, right? It's supposed to look like a mirror image over the y-axis. For the absolute value, that's the v. And that's a mirror image over the y-axis. So that's their symmetry. They have symmetry around the y-axis. But then we also have symmetry about both axes, which we consider symmetry about the origin. And those types of symmetries are displayed in x cubed, or 1 over x is another one of our toolkit functions. But they show us x cubed here. So x cubed, the original x cubed graph, has like a mirror image across the origin, where it follows the same pattern, but in a reflection over the origin. All right. And it keeps its reflection even when you put negative front of the, negative in the input values, or a negative even for the outputs. In fact, you'll notice if you do, this ends up being a reflection across the y-axis. But if you also reflect this one again across the x-axis, this looks like the original graph. And that's kind of on purpose. So this reflection ends up reflecting again, kind of has the same, or does have the exact same graph as the original. That's actually on purpose. That's one of these special symmetries. So let's define them. We actually call these even functions and odd functions. A function is an even function if f of x is the same thing we would get if we plug in f of negative x. So if we get the same value out when we plug in a negative input value, we get the same as we would have plugging in a positive value. That is what we call an even function. The parabola works that way. If I plug in -1, I get the same thing I get when I plug in +1. The absolute value works that way. If I plug in -1, I get the same thing when I plug in +1. So even functions have this great property, and visually they end up being symmetric across the y-axis, or in this case, they say the vertical axis. An odd function ends up being the exact same thing when you reflect it across both axes. That ends up being symmetric about the origin. So this is how we define even and odd functions. If you plug in a negative for x and it stays the same, that ends up being even. If you plug in a negative for x and throw a negative on the outside and it stays the same, that is called symmetric about the origin, or an odd function. So let's look at an example. Let's say I don't want to graph this. I just want to know if it's even or odd. Here's how I would check. First thing I'm going to do, I'm going to plug a negative in the x and see if it comes out the same. So if I plug a negative in for x, that means I'm going to do negative x cubed plus 2 times negative x. Okay, so negative x cubed ends up looking like negative x times negative x times, that comes out negative. So the negative doesn't go away. If I plug a negative in there, because it's 3 times, when I multiply a negative number times itself 3 times, it always comes out a negative. This comes out a negative 2. Now this happens to not be the original function f of x. And because this doesn't equal the original function f of x, this thing is not even. So I've just proven it is not an even function. Okay, let's check odd. So to check odd, we're not only going to plug a negative in for x, but we're also going to put a negative on the outside. So here's how that's going to look. That means if I plug a negative in on the outside, applying a negative on the x is going to look exactly what it was up here. It's going to basically be this. That's what a negative in for x looks like. So negative x cubed minus 2x. To plug a negative on the outside means I'm going to basically distribute a negative into everything. So that ends up being a positive x cubed plus 2x. Okay, that is f of x. That does equal the original function that I have highlighted. So this means it is an odd function. So this is an odd function because when I applied a negative on the outside and on the input, it ends up becoming the original equation. And we'll save stretches and compressions for the next video.